Yeah, good day, call. This morning we'll be talking about recursive algorithms. Now, previously we talked about mathematical induction and recursive induction, and we know that the assumption for induction hypothesis requires that you make it takes three steps. N is equal to 1 if it's true, n equals to k. You substitute your n for k. Then I want to show that it is true for n equals to k plus 1, which follows the hypothesis. Right. So then we also have looked at the recursive induction. But this morning we are looking at recursive algorithm using that same principle. It's built on the principle. Now, don't forget that when we're dealing with sequence and summations, we talked about Fibonacci numbers, and as we know, we use strong induction to prove a result about the Fibonacci numbers. And don't forget that strong induction is not limited to n equals to what? 1. So we do for 2, 3, and above. It must be true. If it's true for n equals to 1, it must be true for n equals to 2 and higher numbers. That's the strong induction. But for weak induction, only relaxes. It stops at n equals to 1, then you fly with it. But not the same with strong induction. But now we are looking at the first thing we're going to be looking at here is the Fibonacci numbers. Now we have our f0, which is the initial value. Then we say our f1 is equal to 1. Then we have a generalized form, which is f of n is equal to f of n minus 1. That is f subscript n minus 1 plus f subscript n minus 2. And that is want to find f2, f3, f4, and f5. So based on the initial value we're given and what f1 is, to get our f2, which is equal to what? f1 plus f0. That is 1 plus 1, f3, f2 plus f1, 1 plus 1 again. We have 2, then f4, f3 plus f2, and on to f5. So that is how Fibonacci sequence works. Now let's look at a recursive defined set and structures. Now example, let's look at a subset of integers s. Now don't forget that in proving strong induction or whatever induction method you want to do, you still have to go through the basis. The basis will tell you that this holds. If it holds for that, then you now proceed to the recursive step, right? So we have the basis says 3 belong to S, or 3 is a member of S. Then the recursive step says if X is a member of S and Y is a member of X, then X plus Y is in S. That is F plus Y belong to S. So we know that initially 3 is in S. 3 plus 3 will give us 6. Right. Then 3 plus 6 is equal to 9. So these are set of, when you had integer to integer, it gives you back an integer. Okay. So that is it. What we have. Then we have the natural numbers n. Let's look at the basis. The basis step says, 0 belongs to natural number. And that is actually true. Then the recursive step says, if n is in n, then n plus 1 is in n. Right. And that gives us 0 plus 1 is in n. Then 1 plus 1 is 2, which is also in n. And that is just what we have been able to show based on our the induction approach. Now let's look at string concatenation. String concatenation. We all know what a string is. So now two strings can be combined, via operation of concatenation. Now let sigma be a set of symbol and sigma star be the set of strings formed from the symbol in sigma. We can define the concatenation of two strings denoted by that dot recursively as follows. The dot there simply means it actually signifies the concatenation approach, the operation for the concatenation. So let's look at the basic step. Basic step says W belong to is a member of what? Sigma star. Then W dot lambda is equal to what? W. That is, that lambda actually is unity. That is 1. So equals to W. The recursive step, if W1 is a member of sigma star and W2 is a member of sigma star and X belong to sigma, then W1 holds. Now let's look at the union, the bringing the concatenation. Now that's what we want to look at. Now let's look at the case where W1 is equal to what? Abra. W2 equal to what? Cadabra. So when we bring them together, it becomes what? Abracadabra, which is a word that people use basically for magic. So, and that is a string. W1 is a string, W2 is a string. Bringing them together forms abracadabra, and that is just that. Now, well-formed formulae on propositional logic, and we know the first lecture we had on this course. In this course, we had logical. We did logic actually. Now, the set of well-informed formulae in propositional logic involving TF propositional variables, that is true and false. An operation from the set, we have our negation, the hand, the or, the implication, then the by implication. These are the symbols we have from left to right. Now the basic step, T, F, and S, where S is propositional variable, are well-informed formulae. Now let's look at the recursive step. If E and F are well-informed formulae, then the negation of E, that is negation on, that is we are negating that E. Right. Now E and F, we can have something like this. We can have E or F. We can have E imply F. We can have the E, the by implication, that is imply E imply F, F imply E. So that's what the by implication means. They are well-informed formulae. So example, we can have this, which is not new to us. P or Q imply Q, and F is well-informed formula. But we have a case of PQ, there's nothing, there's no conjunction, there's no disjunction, there's nothing bringing them together, so it's not well-informed. So that's just an example of well-informed. With what we have earlier for the recursive step is actually telling us what to do. What operation are we performing? Is it disjunction? Is it conjunction? Is it implication, or is it by implication? That one has already given us, is very clear. But the PQ is not well informed, so we don't fly with it. Now let's look at the recursive factorial algorithm. Now example, give a recursive algorithm for computing n factorial where n is a non-negative integer. Now let's look at the solution. Use the recursive definition of the factorial function. Now look at it. The procedure is the factorial n. We define our n to be what? Non-negative integer. If n is 0, then return 1. That is 0 factorial is 1. Else output n factorial. That is, if it's not equal to 0, then we output n factorial, and we are saying that what? N dot factorial n minus 1. So the function there is what? Is n dot factorial n minus 1. At the end of the day, to output n factorial. This can be proven by inductive approach, which we will look into later. Now let's look at recursive exponentiation algorithm. Give a recursive algorithm for computing a raised power n, where a is a non-zero real number and n is non-negative integer. Now let's look at the solution. Now what you're going to do is use the recursive definition of a raised power n. Like we know that a raised power n simply means we can rewrite it in form of a times a raised power n minus 1. That is a raised to power 1, then a raised power n minus 1. You see that one up there, from law of indices, 1 plus minus 1 will become 0. So it becomes what? A raised to power n. That's what we have. But let's see how this translates. So without what, first thing we do is what? The procedure is so that we have power, that is power a is a non-zero real number, n is non-negative, so if n is equal to 0, then we return 1. Depending on the program we are running, if you are running this in Python, for instance, say if n is equal to 0, you put a full colon there, then return 1. Else return a dot power, you can see a comma n minus 1. That will give you a times a raised power. This, the first a in the bracket, and close the bracket, the left a is actually going to carry n minus 1. So at the end of the day, the output will become a raised power n. Just like I explained earlier, a times a raised power n minus 1 gives you a raised power n. You get, so that is it. That's what the algorithm looks like. Okay. Now let's look at the recursive GCD. And what is GCD here? Greatest common divisor. Example: give a recursive algorithm for computing the greatest common divisor of two non-negative integers a and b with a less than b. Solution. Now we use the reduction, that is GCD AB is equal to GCD B modulo A and A. Right. That is, if we look at GCD, for instance, let's look at two numbers, 6 and 9. What is the greatest common divisor there? The greatest is 3. Right. So, and this uses the modulo approach. That is B modulo A, then A. By so doing, it will derive, this particular function will help to derive the GCD for two numbers A and B. Now, and the condition is GCD 0B is equal to B. That is, you know that 0 already is actually there already, right? Then you can see that between 0 and B is greater than 0, right? So that is why GCD of 0 comma B will give you B. That is saying that GCD of, let's say we have I already mentioned a case of GCD of 3 and 6 and 9 to be 3, right? Don't forget that here already we have taken care of the condition is already given. The greatest value enclosed here is the GCD. You can see the greatest value. After taking care of the modulo, you know what modulo is. For instance, if you can remember your binary operation, if I have 4 and I say what? If I say in modulo 3, it will give us 1, right? Because 4 divided by 3 is 1, remainder 1. So we have write the 1 down. So in the case of that, that is what is applicable here. Now the procedure, let's look at the programming procedure. GCD AB, that is non-negative integers with a less than b. If a equal to 0, then return b. Else return GCD B modulo a comma a. At the end of the day, the output will give you the GCD a comma b. Now, like we know that if a is equal to 0, we return b. And that's just like the upper explanation. Okay, now let's go to recursive binary search. Now, what do we mean by recursive binary search? Binary search is to find the target values location in a sorted data set as quickly and efficiently as possible by repeating the search space. Step 1. The steps involved is that, assuming we have a range, a set of data, then what we do is that before we sort the data, right, we'll sort it in either ascending or descending order. And after sorting, we split it into 2. We look at the middle. If the middle is the number we are looking for, then we stop. Otherwise, if the number we are looking for, the target number, is smaller, then we search the left. Right. Then if the target value is bigger than what we have in the middle, we search the right half. So we repeat until the target is found, or the search range is empty, because if it's not found, therefore it doesn't exist. That's what it means. So in this case now, we are looking for 23 in this set of numbers, actually in the middle. So that's what we just pick it and remove. So, and this can also be computed. The algorithm can be constructed. And let's look at the example. We say construct a recursive version of binary search algorithm. We have we assume that we have A1, A2 up AN, and in that order, an increasing sequence of integers. Initially, I is equal to 1, I is 1, and j is n. We are searching for x. We are searching for x. X belongs to that sequence. Now, the procedure involves is that we search I, j, x. Don't forget that we said I is 1, j is n. And we can see the range that I less or equal to I, and is 1 is less or equal to I is less or equal to j is less or equal to n. That is, goes from 1 to n. That it passes through I and j. Okay, now m. Now that is the floor. We can say if I plus j, we divide, we split into 2. We can see the floor is there. Then if x is equal to a subscript m, then return m. Else, if x is less than am and I is less than m, then return the binary search I m minus 1x. Else, if x is greater than a subscript m and j is greater than m, then return binary search. You know, that is talking about if it's not in the middle, if it's greater than xn and j is greater than m, then return the binary search m plus 1 jx. Else return 0. That is, if we can't find it in the left, we can't find it on the right, and it's not in the middle, therefore we return 0. And that is what it means. So output is location of x in a1, a2 up to an, if it appears. Otherwise it's 0. And that is what we do. Now let's look at proving recursive algorithm. Once you prove that it's correct, how do we prove that? Now we know that both mathematical and strong induction are useful techniques to show that recursive algorithm always produce the correct outputs. We know that. Example, prove that the algorithm for computing the powers of real numbers is correct. Now what do? We want to prove this. We have already done that up there, that these are the procedure involved. We say power A such that non-zero real number is non-zero, then n is non-negative integer. If n equals to 0, then return 1, else return a dot power into a comma n minus 1. Then output is a raised to power n. We have this above. But we want to use mathematical induction. So use mathematical induction on the exponent n, the basis. A raised to power 0 equals to 1. What does that mean? For every non-zero real number a and power a comma 0 is equal to 1. We know that what that means. That is a raised to power 0 is equal to 1. That's what this means. So let's look at the inductive step. The inductive hypothesis is that power a comma k, and that's equal to a raised to power k for all a is not equal to 0, because there's no how a equal to 0 to carry something up there. So assuming the inductive hypothesis, the algorithm correctly computes a raised to power k plus 1, and that gives us what? Power a k plus 1 is equal to what? A dot power a comma k. And we can see that if our k happen to be our power, obviously it adds another power to it, which is what? A. So it becomes a raised to power k plus 1, which is already proven. Match sort. Now match sort works by iteratively splitting a list with an even number of elements into two sublists of equal length until each sublist has one element. Each element is represented by a balanced binary tree. At each step, a pair of sublists is successively merged into a list with elements in increasing order. The process ends until sublists have been merged. The succession of merged lists is represented by a binary tree. Let's look at what that means. Initially, we have 2, 8, 2, 4, 6, 9, 7. All these, they are even. That is 10 numbers. Now, how do we split this? We first split 8, 2, 4, 6, 9. We have 5 there. 5 on the left, 5 on the right. Then we split further. We have 3 on the left here, 2 here, 3 here, 2 here. Then these 3 that we have again, we split again. We remove 2 to the left, 1 to the right. Here we have 1 to the left, 1 to the right, because it's even. We can solve. Then here also we keep splitting. The same splitting is like a mirror image of what we have above. So that's a mirror image, and that's what we have underneath. So that is the splitting. Now let's look at recursive merge sort. Now how this perform? Recursive merge sort is a divide and conquer sorting. That is, it involves we divide, then we conquer, and it's such an algorithm that recursively divides a list into smaller sublists until each sublist has one element, and then merges those sublists back together in sorted order. Suppose we have this list now: 38, 27, 43, 3, blah. So we split. When we split this, we have 38, 27, 43. Then 3 goes with the right hand side. Now recursively sort each part. So after the sorting, we can see that this gives us back the same list we have, but in arranged form, in ascending order. And that is what the sorting does. When you sort, when you split, then you sort back, and it gives you exactly as arranged as supposed to be. Now let's look at this is a Python code for recursive merge sort. The first thing we do is to have the merge sort, that is the array. ARR signify array. Then our full column means we want to proceed to the next line there. Then if length, that is len means length, array is less or equal to 1. What we want to check is if the length is less than or equal to 1, that is if it's empty or it has one element. That's what the array is just. So to return ARR, that is the array. Then the mid divided into 2, we have length array divided by 2. We have the left is equal to merge sort. Here we can see the full column is on the left. The mid here simply means I haven't divided the array into 2. We have the mid. Then the right, merge sort underscore sort array, the mid, the other path. Now return sort merge left right, bring them together. Now diff merge sorts A B. So if not A, return B. If not B, return A. If A is called if A of 0 is less than B of 0, that is first element in array of, if first element in array of A is less than the first element in the array of B, what do you return? Return A plus sort, that is the sort merge A B. You can see this one here, like I said earlier, we want to check if it's 1 there. Actually, you can see that if it is 1 element there, then we have a comma B, else return B, that is empty, plus sort, then we merge, and that's just it. That's just the basic way of doing this. So example is what we have above, that was the example that was used here. The same was repeated, something like the same was repeated here. Okay, so if we do this, we are going to, if you are to print this now to give us that result, because it follows that process already stated above. Now let's look at recursive merge sort. Example, construct a recursive merge sort algorithm. Now we begin with list of n elements L, that is procedure merge sort. L is equal to A1, A2 up to AN. If n is greater than 1, then we now have floor of n over 2. That is assuming if n greater than 1, assuming we have n is equal to 2, for instance, that would be what, 2 over 2, it remains 1. So the floor of that is still 1. But if n is 3 over 2, the floor of that is what, is still 1, because 1.5, the floor is 1. So L1, we have A1, A2 up to AM, then L2, AM plus 1, comma AM plus 2 up to AN. Okay, that is, and talking about the recursive approach, you add 1 to the previous one to give you the current. So now let's say L merge sort L1, comma merge sort L2. That is talking about the merging. So this function will actually merge it and pull them in order if we follow this algorithm. And let's look at recursive algorithm in Python. I want to look at a few examples. Now for factorial, n factorial, we say d factorial, we already defined it. We have our factorial n. So if n is equal to 0 or n is equal to 1, Then go to the next step, return 1, because 0 factorial is 1, 1 factorial is 1. Else, you can see the full column there, return n star, that is multiplied by factorial n minus 1. And that is what it means. You know that n factorial, 2 factorial is what? 2 times 2 minus 1 factorial. That's an example. So whatever n is, it will return the factorial. Don't forget that we started with the function factorial. The function there actually helps to define, and you can see how these work recursively, because the factorial has to do with the n minus 1 relies on the n. So that's just it. And if we want to print 5 factorial, this is what we just say. Since we already know that our function is factorial, put 5 here, you print, what we print out is 120. Now let's go to Fibonacci sequence. The Fibonacci sequence, we already defined it. Fibonacci n, right column, full column. There we have, if n is less or equal to 1, return n. Else, return Fibonacci n minus 1 plus Fibonacci n minus 2. Now if you want to do Fibonacci for 6, that will give us what? 8. That is, you know, Fibonacci start with f0, which equals to 0, f1, like that, depending on. So, and that is 8. I think from the first page, that was what was displayed. Now let's go to sum of natural numbers. How do we get this done in Python? Now we're already defining that, okay, sum underscore natural, and that is the function Python sees, and then our full column, so that we're going to the next step, which is if n equals 1, you can see the double equality, full column, stop further recursion, return 1. That is if this happens. Now else, return n plus some natural number n minus 1. So we print, if it's 5, the output will be what? Be 15. And let's look at how that works. If we say sum underscore natural, we put 5 there, that means we're saying 5 plus some natural number 4. 5 plus, like that, it goes on and on and on till you arrive at what? 15. This actually follows Fibonacci sequence, and we can see is recursive. It's recursive in nature. Let's look at power function exponentiation, just like was shown earlier. Now we have the def power base comma exponent. So if exponent, that is exp, the meaning exponential, is equal to 0, then we return 1. As n raised by 0 is 1, else return base times power, then base comma exponent exp minus 1. Then the power, print this power 2, 3. Right. So we can see that where we are starting from, where we came from, is the power up there, and we say base comma exp. So, and that is what we have, and we can see output 8. Now, for example, we want to do power 2, 3. That gives us 2 star power 2, 2. Then following the upper algorithm, the third to the last, is actually what it means. So when we work it on and on, 2 bracket open 2 star 2 times power 2 minus 1 is equal to 2 until we work it down to obtain 8, and that is it. So I believe you have gained something from this lecture, feel free to ask a question in the comment section, and stay tuned to Datalytics. Subscribe, follow, ask questions, engage, and I look forward to having you in the next video. Thank you.